right, yesterday we started working with angle addition, dealing with angle addition. Formulas, once again, you should have on your formula sheet, you should have all your angle addition formulas also on there, along with all the trig identities. Next week we will add to those also, so we will continue to add to the things that we've been dealing with here. Homework for today, you had to deal with some angle addition ideas. If we take a look, a lot of them are very similar to what we have dealt with already. Problem number 2124, the diagram that we had on the notes, is a diagram that you would use for 21 and 24. When we get up to 27, 30, and so on, what I want to take a look at is problem 36, tangent of 75. Tangent of 75. Once again, as we talked about yesterday, we have two triangles that we can find exact values for. We have a 30-60 triangle and we have a 45-45 triangle. We can find exact values for these two triangles. We can find exact values for these triangles. So the values of 30, 45, and 60, we can utilize these triangles to be able to find exact values for. Well, what I'm asking here for, or what we're asking here for, is a tangent of 75. So we have to ask ourselves, what two of these values can we either add or subtract to get the value of 75? 30 plus 45. So we are looking at the tangent of 30 plus 45. If you said 45 plus 30, that's okay. Okay, so we have a tangent of 30 plus 45. Now we have to expand out. What we have is the tangent of A plus B, which is tangent of A plus the tangent of B over 1 minus tangent A times the tangent of B. Okay, we expand out the tangent of A plus B. Now, if we want to, we could take that one additional step here. Here's my A, here's my B. So we have the tangent of 30 plus the tangent of 45 over 1 minus the tangent of 30 times the tangent of 45. As we work through these, I suggest that you write this out so you're not trying to do too many things at one time. Because it's confusing enough, because it's new enough for us that it's going to be a little bit of a difficulty to be able to get through these problems. So the more the things are written out, the easier it is for you to fill in the blanks. Because what we're asking you here for is, what is the tangent of 30? What is the tangent of 45? Those are the two values that we're looking for. So we have value plus another value over 1 minus this value times this value here. The first one we're being asked for is the tangent of 30 degrees. So if we have the tangent of 30 degrees, Ethan Stutz, what's the tangent of 30 degrees? 30 degrees?
Oh, 1 over the square root.
1 over square root of 3. So we have 1 over square root of 3, which rationalizes to what? So we have square root of 3 over 3. Now your tangent of 45 is your 1 over 1. So we have square root of 3 over 3 and 1 over 1 here again. So when we have this 1 over 1, 1 divided by 1 is a value of 1. So we have square root of 3 over 3 plus 1 over 1 minus square root of 3 over 3. To the extent of this problem, this is all the trigonometric stuff that you have to deal with. From this point on, it all boils down to algebraic simplification, where I have to be able to simplify what I have up there. Okay, which tends to be a little bit more of the difficult part of it. You know, when doing problems like this, you make sure you get this down, because this is a correct solution to a point, but it's not simplified down. It's like leaving a fraction as 6 over 12. Okay? When we have a fraction 6/12, we expect you to simplify that down to 1/2 here. Well, when we have a fraction within a fraction, that's called a complex fraction. We need to simplify that down. We have a complex fraction, fractions within the fractions. Now, I know when you're over in Algebra 2 right now, Dr. Reed said that you were going through rational expressions and working through them at this point. So simplifying rational expressions, and this is a complex rational fraction, takes a little bit of work. A complex rational fraction, or a complex rational expression, is a fraction within a fraction. And we need to be able to simplify this down. Well, if I have a fraction 2/3, we can multiply numerator and denominator by the exact same thing and create what is called an equivalent fraction. Okay, it doesn't look the same, but it means the exact same quantity. If I have 2/3 of something, and if I have 8/12 of something, I have the exact same thing. So what we look to do with the fraction within the fraction is we want to clear fractions out. We want to get rid of these fractions within the fractions. And what we're going to utilize is we're going to utilize our distributive property. Now, to utilize our distributive property, what we do is we have one big fraction. That's what I'm going to call this one big fraction right here. And then we have a bunch of little fractions within the big fraction. Okay? What we look at is all the little fractions and get a common denominator between all the little fractions. Well, if I take a look at my denominators, I got a 3, I got a 1, I got a 1, and I got a 3. So my common denominator between all these fractions is going to be what, Ash? What would be our common denominator between all these fractions here, all these little fractions? 3. And we're going to multiply through top and bottom by 3. Just like over here, we multiplied top and bottom by 4. Here we're going to multiply the big fraction top and bottom both by 3. Using our distributive property, I have square root of 3 over 3 times 3. 3's go bye-bye. Second one, we have square root of 3 times 1. I got 3. On the bottom, multiplying through, we have 3 minus square root of 3. So what this allows us to do is this allows us to clear our fractions out. Our complex fraction gets reduced down to just a fraction. But are we there yet? Are we there yet? Are we there yet? Are we done yet? No. But what I suggest that you do, if you have something like this on a test, give me this, and if you have time, come back to rationalize it. A little star beside it so you can remember to go back to rationalize it. Because to rationalize this, that's the last final step. To rationalize, it's only going to be worth 1 point on the test. Okay, for the amount of time it takes, is it worth 1 point? That's up to you. problem we run into is we have a square root on the bottom. Okay, we like to rationalize our fractions, which means when we rationalize the fractions, we get rid of all radicals in the denominator. So we're going to look to multiply once again, top and bottom, by a specific value or a term. To rationalize a denominator, anybody have a guess or anybody know what we're going to multiply our top and bottom by to rationalize our denominator? 3 plus the square root of 3. Anybody know what that is called? We take the exact same thing on the bottom and we just change the sign. Anybody know what these are called of each other? Anybody remember what they're called? They're called a conjugate. A conjugate. Now, what a conjugate does, when we have the exact same things, but we have binomial terms and we just change the sign. That's like a difference of perfect squares multiplication. If I had x plus 2 and x minus 2, I multiply this out, I get x squared. I get plus 2x, I get minus 2x, I get minus 4. The nice thing that happens is this plus 2 and minus 2, they cancel out. These terms cancel out. So we're left with just x squared minus 4. That's what occurs here, and then we'll eliminate our radicals. So what we have to do on top and on bottom is we have to FOIL this stuff out on the top and bottom. We FOIL it out. We have 3 square root of 3. First, let's see, outer square root of 3 times square root of 3 gives me a value of 3. Inner, we get a value of 3 plus 3, which is 9. And last, we get 3 times square root of 3. So we're going to get radicals still left on top. But on the bottom, this is what's sort of nice about what happens on the bottom. On the bottom, we go our first, we have a value of 9. We go our outer, which is plus 3 square root of 3. We go our inner, which is minus 3 square root of 3. And then we go our last, which is minus 3. We have square root of 3 times square root of 3, which is just 3. Like over here, these middle terms cancel out. Plus 3 square root of 3 minus 3 square root of 3, they go away. So combining our like terms here, on top we have 3 plus 3, which is 12. We have 3 square root of 3 plus another 3 square root of 3. That gives me 6 square root of 3. On the bottom, we're left with 9 minus 3, which is a value of 6. Are we there yet? Are we there yet? Are we done yet? No. We're still not there. Once again, a lot of steps to this. If I have that there, you get 7 of the 8 points. Taking it down to where you need to take it down to, you get 1 extra point. I got a common value between all 3 of these values, so we can take a 6 out of all of them. 1, 1, and 2. So we're left with 2 plus square root of 3. We didn't talk about it yesterday, but if you're given the secant of a plus b, we didn't go through any formulas with the secant of a plus b, But we know secant's reciprocal to what, Lucas? Cosine. So we have the cosine, 1 over the cosine of a plus b. So if you have the reciprocal functions, you could just deal with what? You just go back up to the reciprocal functions. I just flip it over. Guys, and all these things that we go through with respect to the formulas, that's what you can do. Let's take a look at problem number 45. Now, what I will do for you is I will keep everything in theta and degrees. I'm not going to go to the extent of radians. We have enough stuff on our plate to begin with. We don't need to go into radians and work with that. So if we take a look at 45, we have the cosine of theta. Let's see, pi over 5, let's see, it's 180 divided by 5, it's 36. So we have cosine of theta, cosine of 36, minus sine theta, sine of 36, is equal to the square root of 3 over 2. Once again, I'm just going to ask for general solutions. I'm not going to ask for quantities here or values, just asking for general solutions. I write A's and B's above my values here because I'm going to run this back into a trig formula. As I talked about yesterday when we solved the problem, what we are looking for is we are looking at the right-hand side of the formulas. And we're trying to take it back to the left-hand side. Can we find a cosine A times a cosine of B minus the sine of A times the sine of B? Which one of those trig formulas is that, Sarah? Cosine of A plus B. That's a cosine of A plus B. So substituting in my A theta, my B 36, what we're left with is a cosine of theta plus 36 is equal to square root of 3 over 2. Now what this takes us back into is this takes us back into problems that we were just solving. We were just doing this when we were dealing with principal values. And to be quite honest, these equations are a lot less complicated than the principal value ones. So solve. What do we do next? We have cosine of theta. We want to solve for theta. We want to get theta all by itself. So the first thing we run into is cosine of theta. So what do we do to get rid of cosine? Now remember, when you do the inverse cosine, you get two values that you have to worry about. You have two values you have to worry about. We have our calculator value, Ethan Stutz, or Ethan Farnsworth. What's our second value? Okay, so we have square root of inverse cosine square root of 3 over 2. You get 30 and negative 30. Principal value, calculated value, and then its opposite. Okay, To finish solving the equation, we have theta plus 36. We have to get rid of the addition by 36. Then just once again, write this in general solution form. I'm not asking for specific values here. Because, you know, to be quite honest, when we put in general solutions, you give me two specific values already. So you should have -6 and -36 plus or minus a period n. Our b value here is a value of 1. Period is 360 divided by 1, or plus or minus 360n. So here's our two general solutions. So once again, you give me two solutions already, -6 and -66, as values that would work for that. Other questions that you have? Once again, this is a little bit nicer for you because you're actually working numbers now. Rather, when you're dealing with trig identities, you're not working any numbers. You're just dealing with proofs with the trig identities. Here you actually get some numbers in there. Okay, we will spend a couple days going over this material and going through these problems. So hopefully you become a little bit more comfortable as you go through the problems. Okay, when I'm giving you these problems, the first thing you need to do is get a picture down before you go any further of what's happening here. I'm giving you the cosine of angle A is in quadrant number 2, and the sine of angle B is in quadrant number 1. So let's get a picture down and do this in the top right-hand corner that you can refer to. You don't have to draw the picture every time. You can just draw it up here in the upper right-hand corner, and then you can refer to it throughout the entire top front page here. In quadrant number 2, I'm going to put angle A. In quadrant number 1, I'm going to put angle B. The cosine of angle A is -4/5. So make an angle A, make the cosine of this angle -4/5, and then throw in your third side. You know, your Pythagorean triples. I try to keep these at Pythagorean triples as much as possible. Once again, we have enough on our plate just working through these. I don't need to throw radicals in here to make them any more difficult. Cosine defined as adjacent over hypotenuse, so we have -4/5. Isaac, what's my third side? We have a 3 here. Angle B, sine of angle B is 5/13. Sine's defined to us as opposite over hypotenuse. I'm hoping as I write that stuff out there, somebody's not sitting going, oh, ooh, I'm not sure about that. I'm hoping that you know the sine is opposite over hypotenuse now, and the cosine is adjacent over hypotenuse. You should know that by now. That should be nothing. You're sitting there going, where do you get that at? Okay, so my opposite has to be 5. My hypotenuse has to be 13, which means my third side, my adjacent side. What's my adjacent side going to be then? At 5, I have 13. My adjacent side is going to be what? Q? What's my adjacent side? 12. We have a 5, 12, 13 triangle. Once again, I try to keep them Pythagorean triples to make this a little bit easier. Okay, let's take a look at problem number 5. Problem number 5. I'm asking you, number 5, the cosecant of A minus B. I have the cosecant of A minus B. Don't have a cosecant formula on my paper, but I know the cosecant is the reciprocal to which function, Maddie? Sine. So this is equal to 1 over the sine of A minus B, which means if I find the sine of A minus B, I could just reciprocate that to find my cosecant. So what I need to do is I need to write out the sine of A minus B. Using only letters, don't throw numbers in yet, expand out the sine of A minus B. Look at your formulas and expand them out. Just using A's and B's. Don't try to throw numbers in yet, because that tends to confuse you a little bit more. Once again, there's too much going on. So just expand out with the sine of A minus B. It takes you an extra 5 seconds to 10 seconds to do it, but it will save you in not making mistakes. And you should have sine of A times the cosine of B minus the cosine of A times the sine of B. Okay, it asks you for 4 ratios. So go up in your triangles. What is the sine of A? What is the cosine of B? What is the cosine of A? What is the sine of B? So you're finding these 4 ratios, 4 fractions from the triangles up above. Paul, what's the sine of A? What's the cosine of B? Then we go to the cosine of A. Skylar, what's the cosine of A? And what is the sine of B? So what we now have is we have 2 fractions here and 2 fractions here. We have to follow our orders of operations. So we need to multiply the fractions first. We need to multiply the fractions first, and then we need to add or subtract. So multiply your 2 fractions together here, multiply your 2 fractions together here. Again, just going across this multiplication of fractions, multiplying across the tops and the bottoms. I'd suggest you don't reduce it down because you're going to have to subtract these. This will always give you a common denominator. So we have 36 over 65 and a minus 20 over 65. Now what you have to watch out for here is we have 36 minus a negative 20 over our value of 65. So we have minus a negative, that gives us a value of 56 over 65. Now that is the sign of A minus B. To find the cosecant of that, just flip it over. So we have 65 over 56. Okay, don't forget to go back and reciprocate it. And it's natural. You go through a whole problem, you figure out the sign of A minus B, and then you forget, oh yeah, I need to reciprocate that, and you forget to. Just a common mistake that occurs there. Take a look at problem number 9 on the back. Once again, I suggest you put an A here and a B here. Your A is your 2 theta, your B is, should be a tangent of 50. Your B is your 50. Your A is your 2 theta. If we take a look at this, we're taking a look at the right-hand side. We're trying to move it back to the left-hand side. Which one of our tangent formulas is this? Is this tangent A plus B or tangent A minus B? A minus B. So this is the tangent of A minus B. So what we have is we have the tangent A is a value of 2 theta, B is a value of 50, is equal to negative square root of 3. Once again, we want to solve this equation. We have the tangent there to get rid of. Ella, what are we going to do to both sides to get rid of tangent? Inverse tangent. So we're left with 2 theta minus 50 is equal to the inverse tangent of negative square root of 3. Which is what, Jacob? Negative 60 degrees. Now, when we dealt with the inverse sine, we had the calculator value, the principal value, and its supplement. When we dealt with the inverse cosine, we dealt with the calculator value, which is the principal value, and its opposite. We never dealt with inverse tangent. What happens with inverse tangent? The inverse tangent becomes a lot easier. If you remember back to sine and cosine and graphing our tangent and cotangent. When we graphed our tangent and cotangent, we had these asymptotes. and we had these graphs here. We graphed a sine or a cosine curve to get to this point. The sine and cosine curve the period was 360 degrees because we had to go up, we had to climb the hill, we had to scream and go all the way down, then we had to go back up again. That was our sine and cosine curve. We use these as our guides to get our asymptotes in here. Once we got our asymptotes, we drew in our tangent curves or our cotangent curves. But if we take a look at our tangent or cotangent curves, how many degrees does it take? The period here was 360 degrees for the sine or cosine, but the period here for one complete cycle for tangent and cotangent is not 360 degrees. How many degrees is it? 180 degrees. Every 180 degrees, the pattern repeats. Every 180 degrees, the pattern repeats itself. So to calculate our period here for tangent and cotangent, we have 180 divided by b, which allows us to then not have to worry about a second value. Because when you're dealing with tangent and cotangent, welcome to Ohio weather. When you're looking at tangent and cotangent, for tangent and cotangent, it's opposite over hypotenuse. We have negative and we have positive, we have negative, we have positive. If I look at my tangent and cotangent, I go negative over positive, then negative or positive over negative. We can just add 180 degrees to get to the next one. Then we can add 180 degrees to get to the next one. Then we can add 180 degrees to get to the next one. We could just keep on adding 180 degrees, and we just go from 2 to 4, or if I want to, positive here to positive here, because we have positive over positive and negative over negative. So I could just keep on adding 180 degrees, and I don't need a second value, because I could just keep on adding 180 degrees and get to the next value. It's not like we had a principal value and its opposite, or principal value and its supplement here. I just go from 1 to 3 or 2 to 4. So I can complete my problem here by adding 50. So we have 2 theta is equal to negative 10, and dividing by 2, theta is equal to negative 5, plus or minus the period n. Well, our b value is a value of 2. So the period is 180 divided by 2, or 90 degrees. So we have negative 5 plus or minus 90n. Once again, tangents are a little bit different than sine and cosine. Sine and cosine, we had 2 values that we had to deal with when we took our inverse sine and inverse cosine. When you deal with inverse tangent, we could just deal with the principal value, because it comes out nicely in the wash for you in regards to, I just can add 180 to get to my next value, or subtract 180 to get to my next value, or the period 180 divided by b. Tomorrow's worksheet is going to be very similar to what we just did here today, dealing with just solving trig equations, working through trig equations, dealing with angle additions. Questions you have? All right, you have about 5 minutes here. The rest of the time is yours.